In the last lecture, I talked about the conceptual idea of model predictive control, and then talked about the notion of an optimization problem that we will solve, the notion of control and prediction horizons, and basically explained how we are going to look into the future and then ensure that the future predictions are as close to the set point values as possible. And to do this, we make what is called a move plan, that is what is the control move that I am going to make at the current instant and also into a certain number of future instants, so that the mismatch between the predicted output and the set point are minimized. In this lecture, we will look at how we formulate this problem in terms of an optimization problem. Since we are going to talk about an optimization problem, I will also give a very quick introduction to how optimization problems are solved. In fact, I am going to just use a couple of slides to quickly show you how these optimization problems are solved, so that you can understand model predictive control in lot more detail, and your understanding about model predictive control can be little more complete. So, that is the basic idea. So, just quickly summarizing from last lecture, we talked about a control horizon, which is having a control move plan. So, basically if I am sitting at time t equal to k, if I am making control move plans, since I am still talking about CISO systems here, I have to make decisions about values of u at m steps, and what those m steps are uk plus 1 and all the way up to uk plus m minus 1. Okay. So, if you think about this, this is the first decision I have to make, what value that should the input take at time k, and the second decision is what value should the input take at time k plus 1, and the mth decision is what value should you take at time k plus m minus 1. So, these are the m values that I have to choose for this control move plan, and since it is a CISO system, there is only one manipulated variable. So, there are m values for this one manipulated variable that I need to identify. Okay. So, that is how this part of the picture works. And now, what criteria will I use to identify these values is where I want to use a criteria where the future predictions are as close to set point as possible. So, how would I decide this? How would I come up with a criteria for to do this is what we are going to see in the next few slides. So, in some sense, if you think of the error as error at k plus 1 is y set point, whatever value I keep, minus y at k plus 1 given k, and error at k plus 2 is similarly y set point minus y k plus 2 given k, all the way up to error at k plus p is assume y set point minus y k plus p given k. So, then basically somehow I have to come up with a criterion which jointly or collectively minimizes all of these values. So, that is the important idea. So, the optimization problem should have some way of jointly or collectively minimizing all of these errors is what we are looking at. So, from an MPC formulation viewpoint, what we are saying is we want to formulate this model predictive control as an optimization problem. Okay. And whenever we talk about an optimization problem, the optimization problem usually has three components. So, if you understand these three components, then you know exactly what is happening. So, there is always an objective function f of x, which is basically scalar function in simple optimization problems. It can also be a vector function when we talk about multi-objective optimization problems and so on, which are all far too advanced as far as we are concerned from this course viewpoint. So, as far as this course is concerned, the objective function is some function of variables, and it is a scalar function. Now, when I say this is a scalar function, this x can be several variables that you are trying to optimize. So, typically an objective function for the cases that we are looking at will look like this. There is some function of x1, x2 all the way up to xn. So, there might be n variables, m variables, whatever it is. So, this is an objective function, and now we call these variables which are part of this function, and we are basically looking for what these variables should take in terms of their values is the thing that we are looking for. So, basically what we are saying is, whenever I have an optimization problem, I have an objective which is a function of several variables, and I am going to make decisions about what values these variables should take. So, these are then called the decision variables, x1, x2 all the way up to xn are the decision variables, and basic idea is I am going to make decisions about these variables such that this function is either maximized or minimized. Okay. So, in other words, what we are saying is what values of these variables will maximize the function or minimize the function. Okay. So, these are called decision variables, and a typical optimization problem also has constraints. The constraints could be these variables have to be between lower bound and an upper bound. So, this is a constraint, or some other functional form which involves these variables are between some values and so on. So, you could have several types of constraints here. So, the constraints are usually on the decision variables themselves or some functions of decision variables. So, it can be either directly on decision variables or some functions of decision variables. Okay. So, that is basically very compact, very quick, simple explanation of an optimization problem. Now, there are several types of optimization problems depending on what type of constraints you have, what type of variables you have, what type of functions you have, and so on, and we are not going to talk about all of those here. So, we are going to keep it very simple, very focused towards the type of optimization problems that we need to solve for solving model predictive control related problems. Okay. So, really the summary of this is that an optimization problem has three components. You have to define an objective function, you have to define constraints, and you have to define the decision variables. And when you actually define the objective function, the decision variables are also defined, because you actually write the objective function in terms of these decision variables themselves. Now, let us see how all of this fits into this MPC formulation idea. Right. Before we do that, let me explain how you find an optimum solution, so that it becomes easy as we go along as far as this model predictive control is concerned. So, again I said f is always a scalar function. This is a function that I am either trying to minimize or maximize. Typically people will talk about minimization problems most of the time, because maximization problems can also be solved as minimization problems. So, you do not have to really worry about whether it is a minimization or a maximization problem, both of these are completely equivalent. So, we will basically only focus on minimizing a certain objective function. So, when you write a optimization formulation, I said f is a scalar variable. Now, within f the decision variables could be one or many. If there is only one decision variable, it is called a univariate optimization. If there are more than one decision variables, let us say even two, then this is called a multivariate optimization problem. Okay. So, more than one or single univariate. So, let us look at a very simple univariate optimization formulation here, and these are some typical ideas that you have seen hopefully in some other course or at your high school level. So, when we write an optimization problem, I mentioned in this lecture that you are going to have an objective function, decision variable and constraint. So, the way you write this is your objective function and this is your decision variable. So, typically you write min, and below that you write the decision variable, you write the function here, and these are constraints. So, x element of real means now x can take any value here, but in some cases you might say x is less than equal to 1, less than equal to 0. Okay. So, this could be a constraint. Okay. So, you can think of any constraint, and as I said before, the constraints are written in terms of the decision variable or functions of decision variables. So, both are possible. Now, you might ask, so what is this optimization problem solving? So, supposing you were to plot this function f of x as a function of x, what this optimization problem is trying to solve is trying to find the value of x star at which the function takes the smallest value, because we are trying to minimize this here, right. So, that point would be this here, because any other x, if you take f of x, will be larger than this. So, the absolute smallest value that f of x can take for this function will occur at this x star. So, when we solve this, what we are going to get as a solution is basically this x star, and once you get this x star, then you can actually find what the minimum function value is by substituting x star in f. So, from x star you will get f of x star, which is the minimum value of the function, but the key result that any optimization problem that we are looking for is the solution, which is the values the decision variables should take, so that the function is optimized, in our case minimized. Okay. So, you can think of an outcome of solving an optimization problem as values for the decision variable. So, this is very important to remember, because when I connect this to control, we are going to write the optimization problem with decision variables which are the move plans, right, the choice for the input values that we talked about, right. So, I have uk plus 1 all the way up to uk plus m minus 1. So, those m variables, if I can find values for that such that some objective is optimized, then I have my move plan. So, that is the connection between control, model predictive control and optimization. So, this is something that you should keep in mind. So, the outcome of solving an optimization problem is the solution, and the solution is basically telling you the values that these decision variables should take, so that objective is minimized. Okay. So, in a simple case, this is called a unimodal function. In simple cases, there is only one optimum solution, which is this, and you can get this x star, but in more complicated cases you could have functions which are like this. These are not unimodal functions, they have more than one minimum. So, if you look at this point here, if you look at in the locality of this point, you will clearly see that this is the lowest value this function can take at this point. So, this is called a local minimum x1 star, and if you look at around this region, then the lowest value the function can take is lower than this, and the decision variable value at which this happens is x2 star. Okay. So, this is called a local minimum, this is called a global minimum. Now, I do not want to get into too much optimization theory. Let me just tell you that it is very difficult once you identify an optimum solution based on certain conditions, which I will show in the next slide. Very difficult to identify whether it is a local or global minimum. You might ask a question saying, why is it difficult? Because if I find this point and then I compute the function value, clearly this point function value is going to be lower. So, this is a global minimum and local minimum. However, the difficulty lies in identifying all these points. So, in other words, supposing you start an optimization problem and then you identify this point based on some conditions. Now, once this point will satisfy all the conditions that are required to be satisfied for a point to be a minimum, and you will get a function value. Once you get this point, you do not know that there is another point that exists like this. So, you have to run an optimization algorithm again to find this point and then compare, right. Till you find all these points, you can never claim something is a local or a global minimum, right. If I had only this point, I cannot claim it is either a local minimum or a global minimum, unless a priori I have proved something, which is again not at the level of this course. But the key point being, once I identify this point, I cannot say it is a local or global minimum unless I enumerate everything else and then find the function values, and then see that this is the absolute low value, then it is a global. If it is not the absolute low value, then it is a local minimum. So, this is another consideration to keep in mind. As far as we are concerned, this is not really an issue. So, we will assume that whatever point satisfies all the conditions for being a minimum, we are going to simply take that and proceed with the control computation. So, that is how we are going to look at when we talk about this optimization from a model predictive control viewpoint. Nonetheless, I thought this is a very simple picture to explain the idea of local and global minimum without going into detail, so that you understand as we start understanding model predictive control itself, that at all points we are talking about local minimum. If the controller formulation is in such a way that I can show that the function is going to be of this form, then we do not have to worry about this local minimum at all, because there is only one minimum, and once you find a minimum, you know that is a solution that you have to live with. Okay, so let us take a very simple example. This is something that would have been taught to you in high school. So I have a function f of x, a decision variable x, and clearly I write the function in terms of the decision variable. Now I want to find a minimum point x star for this function. Then we know from our high school and probably some courses in your college that if you have to get a minimum point, what you do is you differentiate this function with respect to x. So when you differentiate this, you get 12x cube minus 12x squared minus 24x equal to 0. Then you can solve for f prime x is 0, then you will get these three solutions in this case, x equal to 0, x equal to minus 1 and x equal to 2. Okay. So these are three solutions. Now what this means is these three are all optimum solutions. Okay. And based on some calculation, we can either find these to be minimum points or maximum points or what are called saddle points and so on. So the way you do that is the following: you take a second derivative, and then if you take a second derivative of this, 12x cube minus 12x squared minus 24x will become 36x squared minus 24x minus 24. Now when you substitute x equal to 0 in this, you get minus 24. When you substitute x equal to minus 1, you get 36, and when you substitute x equal to 2, you get 72. So now once you get the second derivative, if you want to identify minimum points, whenever the second derivative is positive, these are points that are minimum points. So in other words, of these three, minus 1 and 2 are minimum points, and 0 is a maximum because this is negative, second derivative is negative. So second derivative is negative is maximum, and second derivative is positive is a minimum point. So even in this case, you already see that there are two minimum points. Now if you want to find which is a global minimum, then you have to basically substitute these values. You take these two minimum points and substitute into f. If you substitute x star is minus 1, you will get a value for f of x which is minus 2. And when you substitute x equal to 2 in f of x, you get minus 29 for the function value. So among these two minima points, this x star equal to 2 is a global minimizer of f of x. So this is basic idea of univariate optimization. So take a look at this slide, please go through the derivations yourself, and basically as long as you are able to come to the same conclusions, you have understood very simple univariate optimization. The only thing is this f double prime is greater than 0 for a minimum point, and f double prime is less than 0 for a maximum point. Okay, so these two are minimum points, this is a maximum point. Okay. So this is a very simple idea. Now if the same thing you have to extend it to multivariate case. So when we talk about multivariate, the function is still a scalar function, there is only one f. When we talk about multivariate, now instead of just one decision variable, there will be more decision variables that we have to make a decision about in terms of what values that they need to take. So how is the multivariate case handled is what I am going to show you in the next slide, and that is a simple logical progression of this. I am not telling you why for a minimum point f prime has to be 0 and maximum point f prime has to be 0, and f double prime is negative is a maximum point, f double prime is positive is a minimum point. Why that is all true is something that I am not describing or discussing here. I just want you to understand how these are solved, so that you get a feel for how model predictive control problems are solved in terms of solutions to optimization problems. Now as I said before, if I have a multivariate optimization, again there is only one function, but instead of the function being defined by one variable. In this case the function is defined by both the variables x1 and x2. So, this is a two variable problem. So, let us assume now f is a function of x1 and x2. How do I find out a value for x1 star and x2 star? Because when we have more decision variables, we have to be able to say a value for each one of these decision variables, okay. Only then we solve this problem. So, the idea is very simple. When I had only one variable, it was just f prime x is 0. When I have more than one variable, so basically you do a partial derivative with respect to each of this variable. Dou f dou x1 is 0, dou f dou x2 is 0, all the way up to dou f dou xn is 0. Okay. Now, if I have n variables, I will have n equations, right, because I will have n derivatives to evaluate. If I have two variables, I have two equations. So, in some sense I will have as many equations as variables to solve for. Okay. So, if we apply this, we have to say dou f dou x1 dou f dou x2 is 0. So, in a vector form you can write this as grad f, which is basically writing these two functions one below the other, that is about it, or you can look at them as individual equations and solve, really does not matter. So, when we do dou f dou x1, partial of x1 with respect to x1 is 1, partial of x2 with respect to x1 is 0, partial of 4 x1 squared with respect to x1 is 8 x1, partial of x1 x2 is x2 with respect to x1. So, I have dou f by dou x1 is this, and similarly if I go dou f dou x2, partial of x1 with respect to x2 is 0, partial of 2 x2 with respect to x2 is 2, partial of 4 x1 squared with respect to x2 is 0, partial derivative of minus x1 x2 with respect to x2 is minus x1, and the partial derivative of this with respect to x2 will be 4 x2. So, I have two equations and both of them have to be 0. Now, I have two equations, two variables, I solve this, there is only one solution I get, and this solution could be a maximum or minimum, that you actually identify by doing what is called a Hessian matrix, and this is far too above what we want to teach in this course, but just quickly I will explain this to you. What you do is you do this second derivative matrix. In the one variable case we looked at f double prime x, in this case we look at a matrix which is dou squared f dou x1 squared, dou squared f dou x1 x2, dou squared f dou x2 x1, dou squared f dou x2 squared. So, once you compute this matrix in terms of x1 and x2, you substitute the solution that you get x1 and x2 into this matrix, you will get a matrix like this. Now, simply if this matrix is what we call as positive definite, so if this matrix is positive definite, then this point is a minima, and if this matrix is negative definite, then this point is a maximum, right. So, I am not defining positive definite, negative definite and so on, but this is how you figure out whether this point is a maximum or a minimum point. As far as we are concerned, we know that we can find a solution to as many variables as we want, right. So, this function could be a function of multiple variables. We will never run out of equations. So, if there are 3 variables, then I will have 3 partial derivatives to set to 0. If there are n variables, I will have n partial derivatives to set to 0. So, the one thing that I want you to remember is once I write this objective function in terms of multiple variables, I can always find a solution. Once I find a solution, whether it is a maximum or minimum point, I have to figure out by doing a Hessian and then finding out whether it is positive definite or negative definite. You do not have to worry about this, you simply have to understand that once I have a solution, there is a way to find out whether it is a maximum or minimum, and any software program that you use to solve these optimization problems will be able to do this computation and basically tell you that this point is a maximum point, minimum point and so on. So, this is just to understand that it can be done and the procedure by which a software will do this, but as far as you are concerned, as far as this model predictive control portion of this course is concerned, all we need to know is that we can solve this objective function when it has multiple variables, because this is an important idea, and let me make the connection again. So, the reason why we are interested in multiple variables is because when I am making a move plan, I have variable uk plus 1 all the way up to uk plus m minus 1. Though they all represent the same control input, these are values the control input will take at different points. So, I am going to think of them as separate variables, and then I am going to formulate an optimization problem based on these variables. And I have told you that once I formulate an optimization problem, I can always solve and get a solution to all of this uk all the way up to uk plus m minus 1. Once I get a solution, whether it is a minimum or maximum point, you do not have to worry about that. Whatever programming platform you are using to solve these problems will be able to tell you what that is, and in fact we will work that into the solution process itself. So, now that you have understood basic optimization, how we approach optimization problems, the next step is to really pose the model predictive control problem in terms of the horizon and so on as an optimization problem, and show you how we can solve this optimization problem, so that we can actually get a model predictive controller going. I will see you in the next lecture. Thanks.